Welcome to the lecture demonstration by the Arktemis Group, where our approach to managing water and land resources in water-scarce, rain-fed regions is shared. This video is based on a study led by Sri Vinayak Damle and Dr. Himanshu Kulkarni, focusing on sustainable water and agricultural management in the 3,500 square kilometers Ghod River Basin in Pune, Maharashtra. Today, the fundamentals of stream orders, a cornerstone of sustainable management in low-water areas, particularly in upper river basin catchments, are guided through how our high vertical accuracy geographic information system, GIS, technology delivers precise water supply solutions and engineering designs is also highlighted. Understanding stream orders. Stream orders, a system used to classify the hierarchy of natural water channels from the smallest tributaries to the largest river systems, are explained. This framework is employed to analyze and manage drainage networks effectively, ensuring sustainable water use across various scales. First-order streams. The smallest channels, typically covering 5 to 10 hectares, are viewed as the starting point of water flow, where runoff is formed into defined streams. On the drainage map, these emergent flows are identified as originating from localized sources, such as small farm clusters. Second-order streams. When two first-order streams are converged, they are classified as second-order, covering 25 to 50 hectares. At this level, the catchment area is observed as expanding, and slope changes are noted as becoming more evident, enabling clearer mapping of the basin's structure. Third-order streams. Spanning 100 to 200 hectares, a larger drainage network is reflected by third-order streams. Detailed insights into the terrain and water flow patterns at this scale are provided by slope and basin maps. Fourth-order streams, covering 500 to 1,000 hectares, a more complex drainage network is grown. Slopes and stream paths are clearly delineated on the maps, with the system's interconnectedness highlighted. Sixth-order streams, encompassing 10,000 to 15,000 hectares, a broader view of the landscape is offered by sixth-order streams. Intricate relationships between slopes and basins across these expansive areas are captured by imagery. Seventh-order streams. Spanning 50,000 to 100,000 hectares, significant drainage systems are represented by these streams. The full scope of water movement across these vast regions is illustrated by maps. Eighth-order streams. Covering approximately 350,000 hectares, entire river basins are encompassed by eighth-order streams. At this scale, comprehensive dynamics of water flow and terrain are revealed using mapping technology. Analytical comparisons. To emphasize the precision of our GIS technology, digital elevation models, DEMs, slope maps, and stream order delineations are compared with their publicly available counterparts, with zooming performed from the eighth order back to the first. Digital elevation model, DEM comparison. The DEM, which visualizes terrain elevation, is started with. Using the 5-meter resolution GIS data alongside 30-meter resolution public domain data, significant differences in accuracy are demonstrated. Eighth-order DEM. At the river basin scale, elevation is displayed by the DEM with a color gradient, red for the highest elevations, blue for the lowest, and intermediate colors following a ramp. Finer topographic details are captured by the 5-meter resolution compared to the coarser 30-meter public data. Fifth-order DEM. Zooming to 10,000 to 15,000 hectares, enhanced clarity in elevation features is revealed by the DEM. Superior resolution is reflected by the smoothness of the model, with subtle terrain variations captured that are often missed by public domain data. Second-order DEM. At 25 to 50 hectares, precise hillshades and microtopographic features are identified by the 5-meter DEM with exceptional accuracy, enabling detailed analysis of small-scale drainage patterns. Slope comparison. Slope maps, critical for understanding water flow and erosion potential, are examined next. A stark contrast to public domain data is provided by GIS data, particularly at the dam catchment and river drainage levels. Slope map. Overview. A color-coded system is employed to represent gradient severity on slope maps. Red, up to 3% slope. Orange, up to 5% slope. Yellow, up to 9% slope. Light green, up to 15% slope. Dark green, up to 33% slope. Blue, beyond 33% slope. Detailed analysis, when zoomed into, intricate slope variations are captured by the 5-meter resolution with 95% accuracy, with features revealed that are overlooked by public domain data. Water management interventions, such as contour trenches or check dams, are planned with this precision, tailored to specific terrain conditions. Stream order comparison. Stream order delineations are compared to underscore the superior detail of GIS data. 7th order streams, 50,000 hectares. Up to 7 levels of stream orders are identified by the 5-meter DEM, with intricate drainage networks captured. Only 4 orders are delineated by 30-meter public domain data, with critical tributaries missed. 5th order streams, 3,500 hectares. 5 stream orders are demarcated at this scale using the data, while only 2 are identified by public domain data, with the limitations of lower resolution mapping highlighted. This level of precision is why the model excels. Work with GIS technology is extended beyond mapping. It is addressed to real-world challenges in water-scarce regions. With high-resolution data, the following are achieved. Critical features: mapped, irrigated command areas, surface water zones, and rain-fed regions are identified to optimize agricultural productivity. Recharge zones. Located, areas where water infiltrates the soil most effectively are pinpointed, with groundwater management strategies guided. Erosion controlled. Detailed drainage maps are used to design erosion control measures, such as contour bunds or vegetative barriers. Infrastructure planned. Site-specific solutions like trenches, check dams, and small reservoirs are developed by matching designs to slope and soil conditions. For example, a watershed cross-section is generated using GIS to reveal underground recharge and discharge zones, with water flows enhanced and groundwater managed sustainably. Water availability for agriculture is boosted, resources for businesses are stabilized, and resilient communities are supported by these insights. From a single field to an entire river basin, precision is brought to every scale with the technology. Farmers are empowered to grow more with less water, businesses are provided with reliable resource management, and a pathway to a sustainable future is offered to clients. Water scarcity is transformed into opportunity by partnering with the Arktemis Group. A smarter, more sustainable world with water at its core is built by joining the Arktemis Group.